In this video, we will talk a bit about probability and some of the associated terminology and formulas. If we have a coin, we call it a fair coin if the probability of getting a head when you toss it is the same as the probability of getting a tail. So we would write that as probability of head is equal to probability of tail, which in this case would be 1/2. Now it has to be 1/2 because you have to get one result or the other. It's either going to be heads or tails, and the sum of the probabilities has to be 1. So in this case, if the probabilities are equal, then each of them must be 1/2. If I have dice, then similarly, a fair die, let's say we focus on the 12-sided die. For a 12-sided die, it's a fair die if the probability of rolling 1 is the same as probability of rolling 2, is etc., the same as probability of rolling 12. And since there are 12 possible results and they have to add up to 1 and all of them are equal, then that probability must be 1/12. So let's say I take a bunch of fair dice, 6-sided ones for convenience. Let's say I take 30 of them and I roll them. Then what's the probability of getting some particular result? Well, you might think that because they're fair dice, if I roll 30 of them, then 5 of them should be 1s, 5 of them should be 2s, and so on. But that's only something that's true in the infinite limit. If you roll an infinite number of fair dice, or one fair die an infinite number of times, then you expect equal amounts of all the different results. But if you're just rolling them a finite number, then you can get some arbitrary distribution. There is a chance, however small, that all of them could end up showing 6, or half of them showing 1 and half of them showing 2. Unlikely, but still possible. So let's say I have this set of results, and I want to know if I picked one of these dice at random, what is the likelihood that it is a 4? Well, first I need to organize and tabulate the data. So organize them by number, tabulated the results. So now if I want to figure out the probability, I can say that, oh, the probability of picking one of these dice at random and it having a 4 as the result is going to be the number of dice with 4 over the total number of dice. So in this case, that would be 4 over 30, which would be 2 over 15. And I can do the same for 6, right? Probability of picking one of these dice at random and getting one of the 6 dice is going to be n6 over n total. And so that would be 3 over 30. And so that would just be 0.1. And I can display that graphically. Here I'm displaying the number of dice as a function of the result of the roll. And here in the table, I've added a column for probability, and it's simply the number of dice divided by, with that particular result, divided by the total number of dice. And we can check, and yes, if I add up all the probabilities, they will still add up to 1, which makes sense because if I add up all of them, so then I would get this. I'm summing over all those probabilities, but n total is a constant, so I can pull that out. So then I'm just summing over ni, but the sum of all the ni's is just n total, so I get n total over n total, which is just 1. Here I've plotted the probability as a function of the die result. So it's just this table in graphical form. And you can see that the most probable die roll is 3. It had the most number of dice with that result, 9 dice out of the 30. But if I calculate the average, that's going to be something different. How do I calculate the average value rolled? What I'm doing there is the average result is going to be 1 times the number of dice with 1, plus 2 times the number of dice with 2, plus etc., plus 6 times number of dice with 6, divided by the total number of dice, right? So in this case, it would be 1 times 2, because there were 2 dice with the result 1, plus 2 times 6, plus 3 times 9, plus 4 times 4, plus 5 times 6, plus 6 times 3, all over 30. And if you calculate that out, what you end up getting is 3.5. So we see that the average value of a series of rows can be different from the most likely value. A little bit of notation. So the average value or the mean value of some variable x is denoted by x bar. The operation of taking an average is denoted by the angled brackets. So for a discrete variable, we would say that, oh, okay, x bar is the average value of x, and we take and we find that by doing the result xi times the number of times that result came up, summing all that up, divided by the total number of trials. And because n is a constant, we can move that in if we want to make it the sum of ni over n times xi. But we know that ni over n is just the probability of getting the ith result. So this is summation over I p of xi times xi. Similarly, if we wanted the average value of some other function, say x squared, then we take the average of x squared, and that is simply the sum of the different xi squareds weighted by the probability of each of those results. Another name for the average value of a certain function is the expectation value. So here we talk about the expectation value of x. This would be the expectation value of x squared, and so on. If I calculate that for the set of dice that I had rolled, I have xi, the number of dice with that result, the probability of that result, and the xi squared, right? Simply 1, 2 squared, 3 squared, and so on. The average value of x we saw before was 3.5. The average value of x squared is 14.3. But notice that this is not the same as average value of x, the whole squared, which in this case we would get by simply squaring 3.5, and that's 12.25. So notationally, the way we would distinguish between those two, so average value of x is that, average value of x squared is that, average value of x squared is that. And in general, these last two will not be the same. So be careful with your notation when describing these results. All right, some further terminology. Say a random process has possible results A, B, and C. If A and B cannot occur at the same time, we say that they are mutually exclusive events. So for example, on a coin, getting heads and getting tails are mutually exclusive events. If the result is heads, then it can't be tails, and vice versa. However, on a die, on a 6-sided die, getting a multiple of 2 and getting a multiple of 3 are not mutually exclusive events, since if the die rolls 6, that falls in both those categories. Independent events are not affected by previous events. So for example, if you toss a coin, in general, the result of each coin toss is independent of what happened to the coin previously. So if you repeatedly toss a fair coin, and let's say you get 3 heads in a row, that does not mean that the next toss is more likely to be tails. This is what is called the gambler's fallacy. A lot of gamblers fall to it. They think that it has to correct to the average, so to speak. But no, each individual toss is independent of the ones that happened before. The probability of getting a tail is still 1/2. Probability of getting a head is still 1/2. As a counterexample, if I have 2 red balls and 1 green ball in a bag, and I draw a ball at random, then the probability of getting a green ball is 1/3. If I do not replace the ball, whichever ball it was, red or green, I don't replace it, and then I draw a second ball, then the probability of getting green for the second ball is not independent of the first result. If I got a red ball on the first draw, then probability of getting a green ball for the second is now 1/2, because there's 1 red ball and 1 green ball in the bag. But if I got the green ball on the first draw, then there are no more green balls in the bag, and the probability of getting green for the second draw is now 0. So those are 2 events, the first draw result and the second draw result. Those are not independent. If A and B are independent events, then the probability of getting A and B is simply given by the product of the probabilities. So let's do an example. Let's say I roll a 6-sided fair die 3 times. What is the probability of getting 5 on the first roll, 5 on the second roll, and then any number other than 5 on the third roll? So there are 3 events here. There's the probability of 5 on the first roll, and that is 1/6, right? Because it's just one of 6 possible results. Probability of 5 on the second roll is again 1/6. Probability of anything other than 5 on the third roll. So we're looking for the probability of anything other than 5, so it would be 1 minus 1/6, so it would be 5/6. And so the total probability is simply going to be the product of these 3, so it'll be 1/6 times 1/6 times 5/6. So it'd be 5 over 216. A few formulas and definitions. It's fairly self-explanatory. MAD here is the mean absolute deviation. Basically, what we're doing is finding the absolute value of the difference between xi and the average value of x, adding up all those deviations and dividing by n. So taking the mean absolute deviation. All right, the deviation just be xi minus x, but if you added up all the deviations, by definition, there are as many positive deviations as negative deviations. So if you just added up the deviations, you would get 0, which is why we first take the absolute value of the deviation and then add them all up and take the mean. So we get the mean absolute deviation. The standard deviation, sigma, is another nice and rather naturally occurring thing that again measures how spread your distribution is around the mean. So again, you take the deviation, but this time you square it, right? So that way you don't have to worry about the minus signs. Add up all those squared deviations, take the average, and then square root it. So that's the standard deviation. It's also called the root mean square deviation, which is just sort of a reminder of these operations. So you have the square root, you have the mean, and it's the mean of the squared deviations. So root mean square deviation. And then range is simply the largest xi minus the smallest xi. Now, we've been dealing with coins and dice. They have a fairly small number of possible results. We can enumerate all of them. It's easy. But once you start moving to data that varies more finely or even continuously, well, then you can't show each individual value. So instead, you start collecting the data in bins. As an example, here is some data for over 1,000 baseball players. The name of the player, team, the position, the height, weight, and age. So let's say we take this data and we want to look at the distribution of the ages of the players. We want to see, oh, if I pick a player at random, what's the probability that he's going to be, well, we won't say exactly 30 years old, because that probability is pretty small. We'll say in the range between 30 and 31. Well, what I do is select the data, and I will plot it as a histogram. And so there you have it. You can see that because there are lots of fractional ages, I don't show each individual data point. Instead, I bin them, and I can adjust the size of the bins. I'm going to change the bin width to just 1. So now each column represents 1 year. So you can see, oh, okay, the number of players between ages 20.9 and 21.9, there are 7 of those. Between 21.9 and 22.9, there are 33 of them, and so on. So you can see there's this continuous distribution. And I can change how coarse I want the graining or the binning to be, or I can make it even finer and go for like quarters of a year instead of 1 year. If I want to find the probability of the player being between 30 and 32, for example, so then I would go to this column. I can see that, okay, there's 67 players between 30 and 31, and then 66 players between 31 and 32. And so to find the probability of a randomly picked player being in that range, I basically have 67 plus 66 divided by the total number of players, which in this case should be 1,034 players. So what if we go further into really continuous variables? So for example, you're looking at the position of a particle, and position can vary as finely as you like it. You can measure differences in the range of centimeters or millimeters or nanometers or angstroms. So how do you describe probabilities in such a scenario? Well, let's think about what we did when dealing with electricity and magnetism, when we had to find the total charge of a system. For point charges, we would just add up all the point charges, right? The charge of each point charge, just add them all up, and that gave us the total charge. But when we had a charge distribution, what we did was we defined a charge density and then integrated that to find the total charge. So if you had a charge spread over a line, and you talked about the linear charge density lambda, which might be some function of x, and you would integrate over that line. If you were talking about charge spread over a surface, you talked about the surface charge density, sigma, and integrated over that area to find the total charge. And if you were dealing with a volume charge density, then you would integrate over the volume to get the total charge. So similarly, with probability, we will define a probability density, and we'll denote that by rho. So to draw a comparison between discrete variables and continuous variables in probability, for discrete variables, we need that the sum of the probabilities has to equal 1. For continuous variables, that corresponds to the integral of the probability being equal to 1. Now here I've just said dx, I'm assuming it's probability over a one-dimensional space, but we could have probability over three-dimensional space or two-dimensional space. It depends on the physical situation. For discrete variables, if we wanted to calculate the expectation value of x, we do this sum. And for continuous variables, it becomes an integral. So you have the function whose expectation value you want to find, multiplied by the probability density, and then integrate over the relevant interval. And similarly, if you're doing expectation value of x cubed, take the cube value weighted by the probability of that result and sum it over. Here you do the same thing in integral form. Apologies, there should be a cube inside that expectation value over there. So here's an example problem. Supposing our probability density is confined to the region between minus L and plus L, and we know that the probability density is proportional to x squared, right? It's a function of position. We have that condition that the total probability needs to be 1. So we need the integral of the probability density to be equal to 1. So we need to normalize this probability density. Well, let's try it out. So we know that rho is proportional to x squared. So we'll change that into an equality by introducing a constant. So we say rho is equal to ax squared, where a is just some constant. And then we have the condition that rho dx, the integral, should be equal to 1. And this is the integral over the region minus L to L. So then that becomes integral ax squared dx from minus L to L is equal to 1. And we perform that integral, we get ax cubed over 3, and we're evaluating at L and minus L. And so then that becomes al cubed over 3 minus negative al cubed over 3. And so we get 2al cubed over 3 is equal to 1. And we want to figure out what the value of a is here. So we get that a is equal to 3 over 2l cubed. So putting that back in our original expression, we have rho as a function of x is equal to 3 over 2l cubed x squared. All right, so that's the probability density. But how do we find probabilities from that probability density? Well, probability of what? So let's say we wanted to find probability of finding the particle in the region 0 less than x less than L over 4. Well, what I need to do there is integrate my probability density over the relevant region. So in this case, from 0 to L over 4. So I'll have integral from 0 to L over 4 of ax squared dx. I know what a is. I'll place that in later because it's just a constant, so I'll pull that out. So I get ax cubed over 3, but evaluated at L over 4 and 0. So this is going to be a over 3 times L cubed over 4 cubed, which is 64. And now I can plug in for a. So I have 3 over 2 L cubed, and then times 1/3, and then times L cubed over 60. Times L cubed over 64. The L cubes cancel out, the 3's cancel out, and I get 1 over 128, which is a pure number, which is what you want for a probability. You don't want any units in there, you want just a pure number. So this is how we deal with continuously varying functions, continuously varying probabilities. you define probability density and integrate over the relevant space to normalize your probability density, and then over whatever region you need to figure out the relevant probability. Now, sometimes we have a rule for figuring out probability, but we need to adapt it to a certain situation. So just like we had to normalize the probability density in the previous example, in this case, let's say we're looking at our baseball data and we're trying to pick a pitcher. And from lots of measurements and observations, we have figured out a model for figuring out the success of a pitcher from his height, weight, and age. And the model that we have come up with says that the success of the pitcher is proportional to the square of their height divided by their age. Just a silly model, but sure, let's say we come up with that model. And we have 5 contenders. We have 5 pitchers that we want to pick between. So we need to figure out the probability of each of them winning. Say they're in a pitching competition, and so we want to figure out the probability of them winning. So we apply our formula, h squared over a, we calculate that out. But right now these are numbers with units, they're not probabilities. And to do that, we need to basically rescale everything so that the probabilities add up to 1. So for Daniel Cabrera, for example, we would take this number and divide it by the sum of all these numbers. And so that way we get the probability of success. So get Eric Bedard, 0.17665 Daniel Cabrera, Dan Haran, and so on. And if you add all these up, they will add up to 1 because they have been normalized with that in mind. So this was a bit of a silly example, but let's take a more physical example. In thermodynamics, if you have a system with a set of energy levels denoted by EI, so you have E1, E2, E3, and so on, and the system as a whole is held at a temperature T, then the Boltzmann rule says that the probability of finding your system in energy level EI is proportional to this factor, which is sometimes called the Boltzmann factor. But yes, it's this exponential of negative e to the EI over kBT, where kB is the Boltzmann constant and T is the temperature in Kelvin. It's the absolute temperature. So you can see that if you multiply kB by a temperature, then you will get an energy. And so you have e to the negative EI over a thermal energy. So this is a unitless exponent here, because it's a ratio of 2 energies. But right now, this is just a rule, right? We know the probability is proportional to this. We need to normalize it. So to normalize the probabilities, we define the partition function, z, and that's simply the sum of all these exponential factors. So then the probability is equal to the exponential divided by this normalization factor, z. Let's do an example. The hydrogen atom has a ground state energy of E1, which is negative 13.6 electron volts. And the first excited state is E2, which is negative 3.4 electron volts. And we're going to ignore all the high energy states. If you have a gas of 10 to the 23 such hydrogen atoms, and the system as a whole is at a temperature of 6,000 Kelvin, how many will be in the first excited state? So first we make our life easier by calculating 1 over kBT. So for a temperature of 6,000 Kelvin, this works out to be 1.93 inverse electron volts. And then we calculate the partition function, which is that normalization factor, and it's simply the sum of those exponentials. And it turns out that the ground state energy, which is lower, completely dominates. It's 2.65 times 10 to the 11 versus just 717 for the first excited state. So because of the exponential, even a small change leads to a huge difference. So because of that, when we calculate our answer then is going to be the total number of hydrogen atoms times the probability of finding one in the excited state. And we plug in our numbers and we get 2.7 times 10 to the 14, which sounds like a lot. But when you remember that you started with 10 to the 23 hydrogen atoms, this is really a tiny, tiny fraction. And I had to pick 6,000 Kelvin as the temperature. If I had gone for room temperature, if I had gone for 300 Kelvin, there would be basically zero probability of finding a hydrogen atom in the excited state. Because you can see this exponential is also very sensitively affected by temperature. So if you increase the temperature, that can make a huge difference in the probability. The Boltzmann rule applies to thermal systems at a given temperature. In this quantum physics course, we will determine probabilities using wave functions and Schrodinger's equation and the Born rule. But it's useful to know the Boltzmann rule for when we discuss the experiments that historically led to the rise of quantum theory. They had to explain the results of those experiments. And to understand what's going on there, we need to use the Boltzmann rule. And plus probability shows up anyhow a lot in quantum theory, so it was good to mention this.